Today we are going to read about roles and lagranges theorems. Let us see the first question. Now in first question they have written that Rolle's theorem for the function. Now first let us see the definitions of the Rolle's theorem. Rolle's theorem. Here we have the definition. Rolle's theorem. If f of a comma b, it means f of closed a to b. F of a closed a to a comma b tends to R is a function such that f is continuous on a comma b, f is differentiable on open a comma b, f of a is equal to f of b. Then there exists at least one point C belongs to a comma b such that f dash of C is equal to 0. This is Rolle's theorem. Now let us see Lagrange's theorem, Lagrange's mean value theorem. Now Lagrange's mean value theorem. If similarly, if f tends to closed a f of a closed a comma b tends to R is a function such that f is continuous on a comma b, f is differentiable on a comma b, then there exists a point C belongs to a comma b such that f dash of C is equal to f of b minus f of a by b minus a. So this is Lagrange's theorem. This mean value theorem. So Rolle's theorem has been defined like this. Now let us go to the first question. The very first question is in a model of Rolle's theorem. Theorem given. Wait a minute. Given function f of x is equal to x squared plus 4 in 3 comma 3. This has it to verify the Rolle's theorem. 3 comma 3. So we have to say the definition and follow the rules. Now to write an examination test, consider f of x is equal to x squared plus 4 in minus 3 comma 3. F of x is a polynomial, so it is continuous on R. That means it is continuous on this function already. So continuous. First one is proved, and second one is differentiable. It is also differentiable on R. So this way it is differentiable on this. Again, the third one, f of minus 3 is equal to minus 3 whole square plus 4 is equal to 13. F of 3 is equal to 13. Therefore, f of a is equal to f of b. The third rule is also proved. Therefore, we can say therefore, according to Rolle's theorem, there exists when c belongs to minus 3 comma 3 such that f dash of c is equal to 0. That is, we know that f of c is equal to c squared plus 4. F dash of c is equal to 2c is equal to 0. C is equal to 0. Therefore, Rolle's theorem is verified. Like this, we can first question easily. Now we go to the second bit in this question. Second bit, f of x is equal to sin x minus sin 2x on 0 comma pi. Okay, the second bit, f of x is equal to sin x minus sin 2x on 0 comma pi. Consider this as f of x minus sin 2x. That is first point, and find sin 0 minus sin 0 is 0. Sin 0 is 0. Therefore, it is 0. Continuous. Sin pi, it is 0. Sin 2 pi, 0. 0, 0. Again, it is 0. That's why it is continuous on 0 comma pi. Therefore, continuous. Therefore, according to first point, it is continuous on 0 comma pi. First point is the second one. F of 0. F of 0 is sin 0 minus 0. It is f of 0 is equal to 0 is equal to sin pi 0 sin 2 pi 0. 0 minus 0 0. F of pi. For third point is 4. If the third point is true, the second point will not be true. Therefore, f of x is differentiable on 0 comma pi. According to Rolle's theorem, if it follows the Rolle's theorem's rules, there exists when c belongs to a comma b such that f dash of c is equal to 0. F of c is equal to sin c minus sin 2c. F dash of c is cos c minus 2 cos 2c. Therefore, is equal to 0. Cos c is equal to 2 cos 2c. Cos c is equal to 2 into 2 cos squared c minus 1. 4 cos squared c minus 2 equal to 0. Therefore, c is equal to 1 plus or minus under root of 16 to the 32. So 1 minus under root of 33 by 8. You can see it here. It is, you know, that it belongs to 0 comma pi. Therefore, Rolle's theorem is verified. And that we can conclude it. given function x cube plus bx square plus ax on with c is equal to 2 plus my find a comma b. Given that it holds Rolle's theorem, therefore there exists when c belongs to 1 comma 3 such that f dash of c is equal to 0. Now f of c is equal to c cube plus bc square plus ac. F dash of c is equal to 3c square plus 2bc plus a. It is equal to 0. C is equal to minus 2b plus or minus under root of 4b square for by 6 is equal to minus b plus minus under root of b square 3a by 3. It must be given that c is equal to 2 plus 1 by root 3. Therefore minus b by 3 is equal to 2. That is equal to b is equal to minus 6. B square minus 3a by 3 is equal to 1 by root 3. 9a is equal to 9. B square 36. 36 3s are 18 3s are 9 10. 108 minus 9a is equal to 9. 108 minus 9, it is 99. 99 by 9 is equal to a is equal to 11. So there a and b are 11 minus 6. Therefore we got the respective values. Next question is find c so that f dash of c is equal to f of b minus f of a by b minus a. First one, f of x is equal to a square minus 3x minus 1. A is equal to minus 11 by 11. 11 by 7. B is equal to 13 by 7. Now f of c is equal to c square minus 3c minus 1. F dash of c is equal to 2c minus 3. Is it correct? Yeah, it is correct. Now they have given that f dash of c is equal to f of b minus f of a by b minus a. F of b is equal to f of 13 by 7. It is equal to 13 by 7 whole square. It is 169 by 49 minus 3 into 13 by 7. It is 39 by 7 minus 1 to 49. 169 minus 7 39s are 7 9s are 63. 7 3s are 21. 27 minus 49. Correct. 7 9s are 63. 21, 27. We get it as minus 153 by 49. Now f of a will get it as 303 by 49. Now f dash of c is equal to minus 153 by 49 minus 303 by 49 by, what is b here, 13 by 7 plus 11 by 7. It is 150 plus 300. It is 450 plus 3. 456 by 49 minus by 1014 by 7. 7 14 7. 4 are 28. The 7 9 98. Now minus 456 by 98. It is given by minus 19 by 7. Therefore 2c minus 3 is equal to 19 by 7. 2c is equal to 3 minus 19 by 7. 21 minus c is equal to 21 minus 2 by 7. C is equal to 1 by 7. Similarly, in second bit, we have f of x is equal to e power x and a is equal to 0, b is equal to 1. Now f of 1 is equal to 1, f of 0 is equal to 1, e power 0, 1. Now f of b minus f of a. E. Now c f dash of c to of b minus 1 by c minus, therefore it is minus 1. And now f dash of c equal to e power x derivative is e power x itself. Therefore e power x is equal to e minus 1. Apply log versus x is equal to e power f dash of c, therefore it is e power c. Therefore c is equal to log of e minus 1 to the base e. It is proved. Now we can move to the fourth question. There was theorem for the function x squared. Given function is x square minus 1 into x minus 2 on minus 1 comma 2. 2 vanishes. Simplifying it to x cube minus 2x square minus x plus 2. Now as it is polynomial, it is continuous on R, such is continuous. First point is proved. Second point, f of minus 1 equal to minus 1 square 1 minus 2 minus of minus 1 1 plus 1 plus 2 is equal to 0. Now 2 from 2 8 minus 8 minus 2 plus 2 is equal to 0. Therefore it is true and it is differentiable too. By Rolle's theorem, there exists when c belongs to minus 1 comma 2. F dash of c is equal to 0. Now f of c is equal to c cube minus 2 into c square, c plus 2. C is equal to 3c square minus 4c minus 1 is equal to 0. Now c is equal to 4 plus or minus under root of 16 plus 2 by 6 is equal to 24 plus or minus under root of 28 by 6. It is equal to 2 plus or minus by 3. Belongs to minus 1 comma 2. Therefore all service verified. It's completed. Now conditions for Lagrange's mean value theorem for the following functions in each case. Now let us move to the Lagrange's mean value theorem. The first of all question is x square minus 1 and 2 comma 3. For the conditions of Lagrange's mean value theorem for the following functions. In each case, find the points of theorem. Lagrange's mean value theorem. It is same like our theorem. Since it is polynomial, it is a continuous on closed and differentiable on open 2 comma 3. Therefore, now f dash of x is equal to f of c is equal to c square minus 1. F dash of c is equal to 2c. Therefore, by Lagrange's mean value theorem, there exists one c such that belongs to 2 comma 3 such that f dash of c is equal to f of b minus f of a by b minus a. Now f of b is equal to minus 1. 3 square minus 1 is equal to 8. F of a is equal to minus 1 is equal to 3. Therefore, f dash of c is equal to 8 minus 3 by minus 2 is equal to 5. Therefore, 2c is equal to 5. C is equal to 5 by 2. Therefore, belongs to 2 comma 3. Therefore, Lagrange's mean value theorem is verified. Second question, given that f of x is equal to sin x minus sin 2x. Now it is continuous on 0 comma pi. It is differentiable even to in 0 comma pi. F dash of f of c is equal to sin c minus sin 2c. F dash of c is equal to cos c minus 2 cos 2c. There exists one c such there exists one c belongs to 0 comma pi such that that c is equal to of b minus f of a by b minus a. Now f of b is equal to f of a is equal to 0. Therefore for cos c minus 2 cos 2c is equal to 0. Cos c minus 2 into 1 minus 2 cos square c plus 1 for cos square c minus cos c minus 2 is equal to 0. C is equal cos c is equal to therefore this is verified belongs to 0, 5 belongs to is verified. Now let us go to 6th question. On the curve y is equal to x square, find a point at which tangent is parallel to the chord join 0, 0 and for differentiating on both sides, d by dx is equal to 2x. Given points are a 0, 0 and b 1, 1 for tan theta is equal to dy by dx is equal to x y2 minus y1 by minus x1 is equal to 1 minus 0. Dy by dx is equal to 1. 2x is equal to 1. X is equal to 1 by 2. Y is equal to x square is equal to 1 by 4. It's proved. Now next question, show that the real number k for which equation x square minus 3 let f of x is equal to x square minus 3x plus k is equal to 0. Distribution towards 7. F of 0 is equal to k. F of 1 is equal to k minus 2. Is not possible. No real number k for which f of x has two additional minus 1, 0. No real values of k. So going to 8th question, we have f of x is equal to x minus 1, x into x minus 2, x minus 3. So there is more than one c in 1, 3. That f dash of c is equal to 0. It is continuous. It is a polynomial. It is continuous and a closure 1, 3. It's differential 1, 3. Now f of 0 is equal to